Hello, students. I am Dr. Stuti Singh from ABES Engineering College from Applied Sciences and Humanities Department. So let us continue with the wave optics part 1. Okay, so as we were discussing in the previous lectures, we discussed about interference in thin film, interference in wedge-shaped film, in which we also derived the fringe width derivation, okay, the value of fringe width. Now, in this module, we are going to talk about Newton's ring. Fine. What we are going to talk about? We are going to talk about Newton's ring. Newton's ring and its application. Okay. So now, before we start with Newton's ring and its application, let us talk about necessity of an extended source, because in Newton's ring experiment, the sodium lamp is kept inside a box, and that box is having a broad slit. So now let us understand why in Newton's ring, there is a necessity of an extended source. See, when a thin film is illuminated with monochromatic light from a point source, and it is viewed with a lens of small aperture, the light, if it is reflected from the corresponding points on the film, it does not reaches to the eye. Over here you can see this point it is not reaching, but only these two rays are reaching to the eye. So whole of the illumination is not reaching to the eye if we are using point source. But if we use the extended source, because to see the whole film, the eye will have to be moved from one point to the other. But with the help of over here, I'll be moving the eye from this side, then this side, if we are using pointed source. But if we are using extended source, this situation can be avoided with the help of extended source. Okay, the light reflected by every point of the film reaches the eye easily. The entire film can be viewed simultaneously by keeping the eye at one place only. So therefore, the extended source of light is necessary to the view of film simultaneously. So here also we are going to, in Newton's ring, we are going to use extended source. Now let us continue. Okay. So now for the Newton's, to study Newton's ring, or we have to study the experimental arrangement first. So let us study the experimental arrangement. See, what happens is light from a source S is incident on a convex lens. Okay. Then the light is, collimated or made parallel, and it is incident on a glass plate that is tilted. The light from the glass plate it falls normally. So this is the direction of the light. Okay, it falls normally on a plano-convex lens that is kept above the glass plate. Okay, so whatever the interference is going on over here that we will see in the further lecture, that can be captured back on the microscope. So suppose this is microscope. Okay, so this is glass plate. This is plano convex lens. And this is again glass plate. Okay, so whatever the interference is going on over here, that can be studied. So if suppose this is POQ, that plano-convex lens, and here AOB is the glass plate. Fine. Now let us see how the interference is going on over here in this portion. How we are getting the Newton's ring from plano-convex lens and glass plate. Let us see that. Okay. So this is, if we write this is what? This is experimental arrangement. The above diagram is showing the experimental arrangement. Now let us study the explanation of formation of circular Newton's ring, or how the Newton's rings are formed. Let us continue. So now I will draw only the plano-convex lens over here for the explanation of circular Newton's rings. So let us draw the plano-convex lens and glass plate. Now we can see from the slide that we just discussed before, that the light is formed, it is incident normally on the glass plate and plano-convex lens. Now both are optical instruments, right? And if both are transparent materials, then the rays can be there, from the plano-convex lens, upper surface, lower surface, glass plate, upper surface, lower surface. But over here, which two rays or which rays we are talking about to study the formation of Newton's ring, that we have to discuss. So see, when the light is falling normally on a plano-convex lens from sodium lamp, the ray that is reflecting from the lower surface of the plano-convex lens, okay, lower surface of the plano-convex lens, ray 1, and or we can say reflected ray, and it is traveling inside this air film. You can see that between plano-convex lens and glass plate, there is an air film. So it is traveling inside this air film, and then again it is reflecting from the upper surface of the glass plate. Ray 2. And again, as the microscope is above the film that is being formed over here, it is again known as reflected system. Which system it is known as? Reflected system. Okay. So we are going to study about these rays, ray 1 and ray 2. And this side also, similarly, ray 1 and ray 2. Because see, light is here coming out from here also, the light is coming out from here also, or here. But because of the proper Newton's ring setup, which two rays we are going to talk about for the interference? Ray 1 and ray 2. And again, because of the division of amplitude, easily the interference will occur between these two rays. Fine. So if I label it, it is S, or as we know that it is A, O, B, and P, O, Q is the glass plate. Fine. And from here, we can easily say that this is nothing but the air film is forming at an angle theta. This angle theta is very, very small. Okay, so we can write the path difference for the even these two rays, ray 1 and ray 2. So what will be the path difference in this case? The effective path difference will be delta, if I talk about Newton's ring setup, is equals to 2 mu t plus lambda by 2 plus minus lambda by 2 depending on which which side we are making the geometry. So again, because the light is incident normally, so therefore uh, the value of r will be 0 and cos r will be 1. So this is the part difference. Then what will be the condition of maxima? Condition of maxima will be 2 mu t is equals to, now because we have calculated in thin film, so we can easily write down this. It is equals to 2n minus 1 lambda by 2, and 2 mu t is equals to 2n plus 1 lambda by 2, and the value of n in minus is 1, 2, 3, and the value of n over here is 0, 1, 2, and 3. Now condition of minima. Let us write down the condition of minima. So it is reflected system. Do you all remember what will be the condition of minima? Very right. The condition of minima will be given by 2 mu t is equals to n lambda, where the value of n starts from 0, 1, 2, 3, 4, and so on. So now we can understand that how over here that how circular rings are forming. So I'll make you all understand why the circular rings are forming. See, both the sides of the plano-convex lens, if we draw it very properly, both the sides of the plano-convex lens, if this is T1 thickness, this is also T1 thickness. If this is T2 thickness, this is also T2 thickness, right? And at the center, the thickness is 0. So at the point of contact, if the thickness is 0, there will be the part difference condition will be lambda by 2, because at center, what is happening? At center, T is 0. So path difference will be also lambda by 2. Okay. So, but when the interference will occur, if it would have been a wedge shape, because Newton's ring is an example of wedge shape. Yeah, wedge ban raha hai, angle theta. The angle theta is formed. So it is an example of wedge shape film. But over here, this portion is not straight. So we will not get straight fringes. Whenever the interference will occur, the the ring fringes will turn in this direction, and over here also it will turn in this direction. So as the angle theta is very small, it will be completely forming rings, and we will are getting the circular rings. Okay. So from here, you can understand that every fringe in the locus of points having constant thickness of the air film enclosed between the convex surface of the plano-convex lens and glass plate. These loci are the concentric circles, okay, with the center at the point of contact. Therefore, the fringes that are formed are in the shape of concentric rings with point of contact of the film at the center of the ring. Okay, so this was the explanation. So we can, in short, we can write that the loci from from the plano convex lens lower surface, the loci that is forming is of circle. So we are going to get the concentric ring. Okay. So now let us see the diameters of Newton's ring. So now we will continue, with the discussion of Newton's ring, and let us find out the diameters of the rings that are forming. See, I'm not, just wait, students, there. Diameter of the rings, right? So to find out the diameters of the ring, theoretically, let us draw a diagram. Again, we are drawing a plano-convex lens and a glass plate. Let us complete the diagram. Suppose this is P O Q and it is AOB. So PQ is the plano-convex lens and AOB is the glass plate. Okay, so if we see, I'm again drawing a T thickness on the plano-convex lens. This is the T thickness. Fine. And let us mark this as this is D. Let us draw center. This is E and this is F. Okay, so here it is O, the center, AOB and POQ, it is O. I can just erase from here this O. Let me take the pen. Fine. So mark this as, and suppose over here it is K. Okay, so now if we see this is a circle, so the center of the circle will be somewhere here, right? So from here we can draw the radius of curvature R of the lens that has been cut from the whole this, right? And we can also see that what is T, this is T, right? So if this is T, then what is the value from here to here? Very right. Now this is R, this is also R, so this is 2R. And this is T. The value over here is 2R minus T. Okay. So to evaluate the diameter of bright or dark ring, let us consider a plano-convex lens that is POQ and a glass plate AOB. Let R be the radius of the curved surface of a POQ of the lens and T be the thickness of the film at any point F or D. Fine. So from property of circle, if we see, from property, what we are finding over here is, let us first write down that diameters of bright or not or, we let us write down and dark ring. Okay, so from property of circle, we know that, DE into FE will be equals to OE into EK, right? So now what we will do is, from here we know what is the value of DE and FE. Now, so what we are considering on this thickness, suppose there is a ring that is forming. Okay, what we are considering is on this thickness, suppose there is a ring that is forming. So that ring will be formed on the thickness T like this. The whole ring is formed. So the center of the ring will be somewhere here. And if we see, then what is this? This will be the radius of the ring that is formed on the thickness T. So what is, let us suppose that radius is small r. So no confusion over here. The capital R is, radius of the curved surface of POQ, and small r is the radius of the ring that is forming on the thickness T, that is at FED. The ring is forming. Now this ring can be bright or dark, that we will be seeing afterwards. So the value of O, E to D is R and E to F is also R. Okay, so I'll be writing the same thing, that that DE is equals to FE, that is equals to small r. And what is small r? Radius of the ring that passes through the point F. Okay, the point F or D. Fine. So from here, if we substitute all the values in this equation, okay, suppose this is equation number 1. So if we substitute all the values in the equation number 1, what will it become? It will become, so R into R is equals to, what is OE? OE is T. And what is EK? EK is 2R minus T. Okay, so if we see, then what is it becoming? It is becoming R square is equals to 2RT minus T square. Okay, and since the value of T is very, very less than R, therefore, T square can be neglected. So what will be the value? It means that 2RT will be nearly equals to T square. So what is the value of R square from here? It is 2RT. Or if we say that what is the value of thickness over here? The thickness is R square upon 2R. Equation number 2. And this equation number 2, the value of this thickness is very important to calculate the diameter of bright and dark ring in Newton's ring. Okay. So now let us move further. See, now first let us calculate for, bright ring, the diameter of bright ring. So for bright ring, we have to take the condition of minima that we have written for Newton's ring. Okay, so in that we will be substituting the value of thickness that we have got from equation number 2 when we were solving diameter of bright and dark ring. So what is the condition? So from condition of maxima, it is 2 mu T is equals to 2n minus 1 lambda by 2. Okay. So from in this equation, I'm going to substitute the value of T from equation number 2. So what will it become? 2 mu, very good, R square upon 2R is equals to 2n minus 1 lambda by 2. So from here, I can calculate because you have to calculate the diameter of the bright ring. So what is R? R is the radius of the ring. So over here, we have put it in the condition of bright ring or, constructive interference. So over here, the R is the radius. So let us make the whole equation turn towards the radius. R square is equals to what? 2n minus 1 lambda R upon 2 mu. Okay. So now just look here, students, that lambda is constant, r is constant, mu is constant, because suppose that there is a air film of refractive index mu. No doubt over here it is air film, the value of mu will be 1. And 2 is also constant, so r is depending on n. So I can put a suffix on this r, considering if what to be considered, if nth ring passes through D or F, then Rn square is equals to 2n minus 1 lambda r upon 2 mu. Okay, so what is diameter equals to? Diameter is equals to dn square is equals to 2 into 2n minus 1 lambda r upon 2 mu. So from here we got the equation for the diameter of bright ring, right? Diameter of bright ring. Let us move further. So I can also write, because between plano-convex lens and glass plate, what is forming? It is an air film is forming. So for air film, what is the value of mu? Mu is 1. So what diameters now turn out to be? That dn square is equals to 2n minus 1 lambda r, or dn is equals to under root 2n minus 1 lambda r. So if I can write this as k under root 2n minus 1, where the value of k is under root 2 lambda r. Okay, and n stands for 1, 2, 3, and so on. So what conclusion we can draw is that the diameter of bright ring are proportional to the diameter of bright rings are proportional to the square root of odd natural numbers. And this is a very important conclusion that we can see from here, that dn is equals to k under root 2n minus 1. Okay, so this is a very important conclusion. The question is also asked from this conclusion, show that the diameter of bright rings are proportional to the square root of odd natural numbers. Okay, so this is an important conclusion. So in the next lecture, we will be calculating the diameter for dark ring, and we will also see the application of Newton's ring.